So in this video, we're going to start chapter 2. And chapter 2 starts with Dalton and goes through the postulates of Dalton's atomic theory. So that's going to be the first part. And then after that, we're going to get into more about atoms. So subatomic particles, atomic number, mass number, that sort of thing. So first part, Dalton's atomic theory. So John Dalton was one of the first to come up with the theory of an atom. And he came up with this in 1807. And I don't really care so much that you memorize that number or that date. I'm just including it for reference because as I go through his postulates, keep in mind that we have learned a lot about atoms since 1807. So a couple of these aren't completely correct, and if we were in class, I would always ask which one is incorrect as we go through it. So just kind of keep that in your mind. Since you have had chemistry before, one of these should kind of jump out at you as not being quite right. But we're going to go through them as Dalton stated them in 1807. Depending on what source you look at, you may see these postulates listed slightly differently. Like our textbook actually writes them out a little bit different than I'm going to. They all essentially mean the same thing. It's just depending on your source. Sometimes they'll be explained a little bit different. But this is the way that I tend to go through them. It makes the most sense to me. So essentially it's 5 statements that describe matter. Remember, chemistry is the study of matter. And our first one is that matter consists of tiny particles called atoms. And this statement goes on to say that atoms of a given element are identical. Our second statement says that each element contains only one type of atom and that it is characterized by the mass of its atoms. So each element contains only one type of atom. So the element carbon only contains carbon atoms, the element iron only contains iron atoms, and so on. And it's characterized, by it I mean the element, by the mass of its atoms. So each element contains only one type of atom, and it's characterized by the mass of its atoms. Our third statement, atoms of one element differ from atoms of another element. So while carbon is only made up of carbon atoms and the element iron is only made up of iron atoms, carbon atoms are different from iron atoms. We could say no two elements are alike. Number 4. Two or more different elements can combine. We should actually say, sorry guys, atoms, throw this in here, atoms of two or more different elements can combine in small whole number ratios to form compounds. And we defined a compound as one of our classifications of matter in our first chapter, right? We had pure substances and mixtures, and a compound was a pure substance, and we said it was made up of atoms of more than one element. So atoms or two or more elements can combine in small whole number ratios to form compounds. The new part to this, because we already know what a compound is the small whole number ratio part. So no fractions of atoms, right? We can have one atom or two atoms or three atoms, but they have to be whole numbers, right? We can't have half an atom or 0.624 of an atom. So no fractions of atoms. Only whole numbers. And then our last statement is that chemical reactions involve the rearrangement of atoms, not the creation or destruction of atoms. So if we have a chemical reaction, we're going to, if you have, that chemical bond in one compound on our beginning material, we can break that, we can rearrange how they're connected, and we can form new chemical connections. But we're not actually just all of a sudden making carbon appear out of nowhere or destroying carbon or any other atom for that matter. So chemical reactions involve the rearrangement of atoms not the creation or destruction of atoms. And keep in mind here, we're talking about chemical reactions. In 152, you're going to have a chapter on nuclear reactions, and that's going to be different. Chemical reactions and nuclear reactions are not the same. But chemical reactions, we're not going to create atoms or destroy atoms. We're just going to rearrange how they're connected. And one of the other things that we talked about in chapter 1 was the law of mass conservation, right? We said that the mass of our starting material needs to be equal to the mass of our ending material. Well, if we're not creating atoms or destroying atoms, we're just rearranging them. That's why our mass is conserved, right? If I have 3 carbons, I need to end with 3 carbons because I'm not creating carbon or destroying carbon, or what other element you want to use as the example. So remember our law of mass conservation that comes directly from this statement. Right? If we're not creating or destroying mass in a chemical reaction, right, matter in a chemical reaction, then our mass is going to be conserved. So of these, what do you guys think? What's the thing that's a little screwy? Yeah, we can actually point out 2 here. Atoms of a given element are identical. That's not true. We know about isotopes now. We didn't know about isotopes in 1807. And if you don't remember what an isotope is, we will define that in this chapter. But isotopes are atoms of the same element that actually have different mass numbers. They actually have different masses. And that's, we could go down here and we could say characterized by the mass of its atoms. Not all atoms of a given element have the same mass. We're actually going to characterize it by the number of protons in the nucleus. So atoms of a given element are identical. That's part of his statement, so I don't really want to cross it out, but do know that this doesn't consider isotopes. I guess maybe I will cross it out for effect. It was one of Dalton's statements, but again, we didn't know about isotopes in 1807. I say we, but we weren't around in 1807. Characterized by the mass of its atoms, it's actually going to be characterized by the number of protons. different isotopes have different masses. So if you're going to account for isotopes, then you need to account for the fact that the mass isn't the same for all atoms of a given element. But matter does consist of tiny particles called atoms. Atoms of a given element are very similar. They have the same number of protons in their nucleus. Each element contains one type of atom, characterized by the number of protons. Atoms of one element are different from atoms of another, true. Atoms or two or more elements combine in small whole number ratios, so no fractions of atoms to form compounds. And then when we have a chemical reaction, we're just rearranging how the atoms that we already have are connected. We're not creating them or destroying them. In effect, we're going to conserve mass. So the next part I want to go through are our subatomic particles, or the parts of our atom. So an atom is, like, if you were to take an element and break it down into smaller and smaller and smaller and smaller pieces, the smallest particle that we can get that retains the properties of that element is our atom. Now we can, however, break our atom down into smaller pieces. It's just once we do that, it's not specific to that element, right? It doesn't have the properties of that element anymore. So atoms, they're composed of three different types of particles. So composed of three types of subatomic particles. And what makes one type of atom different from another type of atom is the number of subatomic particles that it has. So hydrogen is going to have a different number of subatomic particles than iron is, and iron is going to have a different number of subatomic particles than aluminum or carbon. So composed of three types of subatomic particles, and then we get the different types of atoms by playing with the numbers of subatomic particles. So composed of three types of subatomic particles. Right? Different atoms have different numbers of these. So what are our three subatomic particles? Yeah, so hopefully you guys are thinking protons. And I'm going to make a little table here. We also have, what's next? Yeah, neutrons. If you said electrons, you're right. I'm just doing them in a different order than you. So all of our atoms are made up of protons, neutrons, and electrons. And then by playing with these numbers, right, by changing them, we get different types of atoms. So I'm going to make a table. I'm not very good at drawing straight lines, but here I'm going to have its electric charge. And then I'm going to have relative mass. And then location. So protons, what is my charge on a proton? Yeah, good. +1, right? Some of you might just said positive, but make sure you say +1 because +2 is still positive, right? It has a +1 charge. How about a neutron? What's the charge on a neutron? Yeah, good. They have no electric charge, so no charge. You could say 0, that would be fine. So neutrons have no charge. I'm sure you guys have heard the neutron joke 1,000 times, right? So like a neutron walks into a bar and says, "How much for a beer?" And the bartender looks at him and says, "For you, no charge." Electrons, what's my charge on an electron? Yeah, good, -1, right? Not just negative, because -3 is still negative, -1. Cool. So protons have a +1 charge, neutrons have no charge, and electrons a -1 charge. So relative mass, by relative I mean comparing them to each other. So I will get us started, because if I don't give you a number, how do we compare them to each other? So I'm going to say that a proton is about 1. And we could put a unit on there if we want, but I just really want to compare them to each other. So if a proton is about 1, what is the mass of our neutron? How similar is it to the mass of a proton is essentially what I'm asking. Yeah, also about 1, right? The mass of a neutron and the mass of a proton are very, very similar. If we were to actually measure them in atomic mass units, a proton is 1.00727, and then a neutron is 1.00866. So if you were to round them both to 3 significant digits, they would round to 1.01. So they're both about 1. They're not the same, but they're very close to each other. So about 1 each. How about an electron? Don't tell me they don't have mass either, because they do. They have mass. A lot of times coming out of high school, or sometimes even a 130, depending on who your instructor was, will say that they don't have mass. They do. Yeah, it's really small. So the mass is probably, I usually write about 2,000 times less. It's probably closer to 18 times less, or 1,800 times less. But we could say it's about 1 over 2,000 if we were to round to just one significant digit. So it's really, 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 really light, right, compared to that of a proton and a neutron. So often we'll say that it doesn't have mass. It does. It's just that the mass is negligible, right? It's so light compared to that of a proton and a neutron that it doesn't really factor into the total mass of our atom. I kind of like, if I was to get on a scale and weigh myself, right, and then write down my mass, and then a fly was to land on my shoulder and I get onto the scale with the fly, and I weigh myself, and then I write down my mass, I'm probably going to write down the same number, right? The fly is not really changing the mass of me at all, because relative to me, it's so light. But is that fly made up of matter? Yes. Does that fly have mass? Yes. It's just that compared to me, it's negligible. So electrons do have mass, but oftentimes we're just going to ignore it completely. We could say that it's negligible compared to that of a proton or a neutron. Again, has mass, but oftentimes we just ignore it completely. Let's actually, I started using abbreviations and I didn't give them to you. It's usually a P for proton. Sometimes it'll be a P with a plus charge. I usually don't put the plus charge there, but if you see that, that is an acceptable abbreviation for protons. Neutrons, lowercase n, and then electrons almost always has that -1 charge. So all of those are lowercase p, lowercase n, and then the lowercase e with the negative charge. Location, where are protons found? Yeah, good, nucleus. Neutrons, nucleus also, very good. How about an electron? And you don't have to get specific. You can be super general here. You actually have in chapter 3, we're going to go into a lot of detail, more than you probably want to do, as to where electrons are. But for now, just super general. Yeah, some of you guys might be thinking electron clouds or electron shells or energy levels, and all of you are correct. I'm going to go even more general with that, and I'm just going to say not in the nucleus. So outside the nucleus. So my protons and neutrons are in the nucleus, the electrons are not. That's all we're really looking for at this point. So protons, a +1 electric charge, found in the nucleus. Neutrons, no electric charge, also found in the nucleus. The mass of a proton and the mass of a neutron are very similar to each other. So overall, my nucleus has a +1 charge, right? Because it has positively charged particles, and then it has other particles that have no charge. So my nucleus is positively charged. And then outside of that, I have incredibly light particles, right? And they have a -1 charge. So most of the mass of my atom actually comes from the nucleus, because we had said that we can often just ignore the mass of our electrons. So let's write a little bit more about that nucleus. So this is the I'm gonna get crazy here, very, let's do one more for effect, very dense center of the atom. Remember, dense meant how tightly those particles are packed together, right? It was the amount of mass relative to the amount of space that it takes up. So if this is very, very dense, what I'm saying is that it has a ton of mass, right? If we go back up, almost the entire mass of our atom is found in that nucleus. So very massive, but its volume is very small. So it is incredibly dense. It contains almost all the mass of our atom, but its volume is tiny, super tiny. So those guys are packed in there. They are super crammed into that nucleus. So the very, and you could probably go on for like 3 pages of varies and honestly not be exaggerating. So the very dense center of our atom. It contains the protons. We're being redundant here, but let's be complete. And neutrons, which means it has a positive charge. I'm not putting a number there because it's going to depend on how many protons it has, right? If it has 2 protons, it's going to have a positive 2 charge. If it has 10 protons, it's going to have a positive 10 charge. So it is going to be positively charged. How positive, again, depends on the number of protons. And then it contains almost all of the atom's mass, right? My electrons do have mass. They're outside of my nucleus, but very light, right? Negligible. The analogy that's often given, and there's a couple of them, but for kind of the size of an atom, like if you see pictures of an atom, right? Like they'll do that as the nucleus, and they'll do, I can't draw, sorry guys. It was supposed to be beautiful. So if you see, and they'll like show some particles, and that's my nucleus, and they'll do like these circles around it, and that's supposed to be an atom. Not even remotely to scale, like so completely far off, it's not even ridiculous. So kind of an analogy is if you took a big football stadium, I forget what they renamed it, the State Farm Stadium, is that the one where the Cardinals play? So if you were to take a big football stadium like that and say that's your atom, then the nucleus is the size of a pea in the center of that stadium. And that pea contains almost all the mass, right? So very, like I said, you could go on for pages with varies and not be exaggerating. It'd be like if you took the entire mass of that stadium, but it was all in that pea, right? That pea weighed the same thing as that entire football stadium. Like that's crazy to wrap your head around, right? That tells you how off scale this thing is. It's not even remotely close. Another analogy is that if the nucleus was the size of a period, like in a textbook, like just a little dot, then the first energy level is 11 feet away. Like totally not to scale. But we can't draw that. There's no way to draw a nucleus and the electrons on the same page and have it to scale. So all the pictures that you guys see are just totally wrong. But it's the only way we can artistically draw them and be able to do it on a page. But just know this, right? I want you to have in your head an accurate representation of what the nucleus actually is. So I'm just erasing this to make us some more room here. So atomic number. So the symbol we'll often use for atomic number, and I actually don't often use it, but you'll see it, is a capital Z. Oh, I'll usually cross my Z's, by the way. This is how I make a 2, and this is how I make a Z. Like, you can't tell the difference. So my Z's, I will cross them like this so you can tell the difference. So this one is a letter Z. This one is the number 2. So atomic number, abbreviated by a capital Z, this tells us the number of protons in the atom's nucleus. So if it has atomic number of 2, then it has 2 protons in the nucleus, right? If it has an atomic number of 20, it has 20 protons in the nucleus. So my atomic number tells us the number of protons in that atom's nucleus. And if you remember when we were talking about Dalton's theory a few minutes ago, I said the number of protons is what tells us what type of atom it is. So atoms of a given element are defined by the number of protons in its nucleus. And this is really important. So atoms of a given element are defined by the number of protons in its nucleus, right? Like if I was looking at carbon, right, I write down a C for my atomic symbol, but there's no little C floating around in space combining with other letters to make things, right? That doesn't exist. What I have is an incredibly dense center with 6 positive charges in it, probably 6 particles that don't have a charge, but that could vary because we have isotopes. And then way, way, way far away, right, relative to the size of that nucleus, I have some electrons. Likely 6 of them, but it could vary. So atoms of a given element are defined by the number of protons. If you change the number of protons, you change what type of atom it is. So carbon has to have 6 protons. If it doesn't have 6, it's not carbon. So if we write down carbon and we put like a 6 here to tell us the number of protons, we're being redundant because that C can't be there if there isn't a 6 there. And if that 6 is there, then that C has to be there, right? If I was to change that to a 7, right? Say I have 7 protons, I now have nitrogen. I don't have carbon anymore. And if I was to lose a proton and say I have 5 protons, I now have boron. I don't have carbon anymore. So if you change the number of protons, you change what type of atom it is, right? It belongs to a different element. So different elements have a different number of protons in their nuclei. Right? If we go back up to Dalton's atomic theory here, make you guys dizzy by scrolling so fast, right? It's characterized by the number of protons, right? Each element contains only one type of atom, and it's characterized by the number of protons. You change the number of protons, you change what it is. It's an entirely different type of atom. Atomic numbers are on the periodic table, and that's how I knew these numbers, because the periodic table tells me. So atomic numbers are listed on the periodic table. And those are the whole numbers and the ones that go sequential. So these are the sequential, and I'll pull up the periodic table here in a minute. So these are our sequential whole numbers. And they have to be whole numbers. We can't have fractions of subatomic particles. I can't have 0.1, protons, or half a proton, or 0.75 protons. I can have 1 proton, or 2 protons, or 3 protons, or 0 protons, but I can't have fractions. So these are always going to be whole numbers. They're counting numbers, right? If we were to actually count the number of protons, so they're exact. Remember, exact numbers come from counting or definition. So let's pull up our periodic table here real quick. So these guys, let me just zoom in it a little bit. These whole numbers. So the 1, we go over to here, 2, So hydrogen has 1 proton, helium has 2 protons, lithium has 3, beryllium has 4. Here's the ones we used as our example. Boron has 5, carbon 6, and so on. If I asked you how many protons in iodide, you would go and find iodine in the periodic table. It has a 53, so 53 protons. How many protons in silver? What's my atomic symbol for silver? Yeah, silver is Ag, so I find that here. Silver has 47 protons in its nucleus. So these whole numbers that go in order on our periodic table, that tells us the number of protons, right? That's my atomic number. The other number that we often consider is our mass number. Let's actually write number out. So atomic number, right? Capital Z, mass number. I don't really use this very often, but if I was to abbreviate it, capital A. Now be careful. These ones are not on the periodic table. The other number, if I go back to the periodic table, that's on it are not mass numbers. So if we look, there's these numbers on here. These are not mass numbers, so be careful. Those are something else, and we will talk about those in this chapter, but they are not mass numbers. In fact, let's write that first. This is honestly the biggest mistake that students make in this section is they go to the periodic table and they tell me that those are the mass numbers. They are absolutely not the mass numbers. So these are not, I'm going to make this huge, not, and I'm going to put a little frown face here so nobody gets it wrong, on the periodic table. I am not following my own netiquette rules here by capitalizing. Right? It means I'm yelling at you. I promised I would never yell at you, but I kind of am. These guys are not on the periodic table, people. Don't forget it. So mass number, not on the periodic table. What the mass number is it's the number of protons plus the number of neutrons in the periodic table. And I just got done saying that we couldn't have fractions of subatomic particles, right? I can have 1 proton and 1 neutron. Just like I can't have 0.75 protons, I can't have 0.75 neutrons. So if we go back to the periodic table again, and you look at these numbers, let's make them really big, they're fractions, right? They're decimals. There's no way I can have 0.0122 subatomic particles, right? These are counting numbers. Mass number is not the one on the table. So I'm counting the number of protons and the number of neutrons. They're going to be whole numbers. They're going to be exact. They're going to have an infinite number of sig figs, right? If I look at this one, I can't have 0.305 protons or neutrons. It's not possible. And that's how we're going to remember it, right? Just remember what mass number is. And then these other numbers in the periodic table, it just makes no sense for it to be a mass number. So mass number, not on the periodic table. What is it? It's the number of protons plus the number of neutrons in the atom's nucleus. Again, it's a counting number, right? If we were to physically count the number of protons and the number of neutrons, right, the total number of particles essentially in the nucleus, this is what we get, right? These are going to be whole numbers. No fractions, right? I can't have a part of a subatomic particle. We'll do some more exclamation marks here. So no fractions of subatomic particles, always a whole number. How would one know the mass number? Well, either I would have to give it to you, or I would have to give you the number of neutrons, and then you can add it to the atomic number, right, which is the number of protons, to get the mass number. Some typical notation is if I give you an element, and I'm just going to use, I guess we shouldn't use Z. I'll just use X as a generic atom. And then sometimes as a superscript, the mass number will be written. And then if one was to put the atomic number on there, it would be a subscript, kind of like I did up here, right? Here I did those as subscripts. Honestly, I'm not going to include that the number of protons, that atomic number, because you have a periodic table, and to me it's redundant, right? Just like I said, if I was to put a C here and put a 6 here, like there's no other option. There isn't another number I can put there besides 6 if I was to put a C. So if you know C, you know 6, right? Putting both of them there is redundant. So I'm really never going to do that, but I will give you mass numbers because you wouldn't know them otherwise. So if I put a 13 here, that tells me my mass number. So since we have this here, if I have carbon, how many protons do I have? You can look at your periodic table, or you can remember what I just erased. Good. So these guys have 6 protons. I know that because we look at the periodic table and it has a 6 above it. And then how many neutrons does it have? Remember that this, right, this is my mass number. And that's my number of protons plus my number of neutrons. So if my mass number is 13 and I have 6 protons, 13 minus 6 gives me 7 neutrons. So my mass number, number of protons plus the number of neutrons. I said I would review isotopes. Right? This was the part of Dalton's theory that isn't correct today. And isotopes are atoms of the same element. So if they're atoms of the same element, what's the same about those atoms? What do they have in common? Yeah, they have the same number of protons, right? Remember, if you change the number of protons, you change what it is. So if you have atoms of the same element, they have to have the same number of protons. Otherwise, they would not be atoms of the same element. They would be atoms of different elements. So atoms of the same element with different mass numbers. And since they have different mass numbers and their number of protons are the same, what's different? Yeah, good. Different number of neutrons. Because they have a different number of particles in their nucleus, their actual mass, if you were to weigh them, is different. So if we go back up, make you guys dizzy again, go all the way back up to Dalton's theory, the part we crossed out here, right? They are identical. They're not, because carbon 12 and carbon 13 are both carbon atoms, right? They both have 6 protons. And then we said characterized by the mass. Carbon 13 and carbon 12 are going to have different masses because they have a different number of particles in their nucleus. So again, we didn't know about isotopes at the time. They're characterized by the number of protons in their nucleus. So back down. And carbon 13 we have there, I just mentioned it. And then carbon 12. And there is a carbon 14 also. It's really not very abundant. It's like trace amounts in nature, but it does exist. So these would all be isotopes of each other, right? They all have 6 protons because I have a C for all of them. And then 13 minus 6 is 7, so 7 neutrons. 12 minus 6 is 6, so 6 neutrons. 14 minus 6 is 8, so 8 neutrons. So these guys have the same number of protons, right? They're all carbon, so 6, but they have a different number of neutrons. So the relationship between these is these would be considered isotopes. So atoms of the same element, all have the same number of protons, but different mass numbers. They actually have different masses. So let's go through some examples. You are going to need your periodic table for this. If you don't have it handy, please put me on pause and then go grab it. And then I'm going to make a big table. So I'm going to have, how are we going to do it? Let's do atomic number. we'll have the number of protons. Let's have our number of neutrons. I'm going to throw electrons in here. We haven't talked about those. We'll do those quick before we do our example. Number of electrons, and then our mass number. And then, sorry for like our incredibly messy table. So we'll do atomic symbol here. It just keeps getting worse, doesn't it? Okay, so just bear with me as I make some of these up. So let's do atomic number of 26, and we'll do 30 neutrons. Let's have a mass number of 21 and 20 electrons. And atomic symbol of PD. Make sure your first letter is capital and your last letter is lowercase. And 107. Let's do one more. We'll do NI, capital N, lowercase I. And the number of neutrons, 32. Okay, so what we're going to do is we're going to fill in the missing pieces. I do have electrons on here, so we're going to throw that real quick. For neutral atoms, and we're only going to deal with neutral atoms right now because I have not talked about ions. So we can do another table like this after I talk about ions, and then that column is going to be a little bit different. But for neutral atoms, and by neutral I mean it's uncharged, right? If it's uncharged, then my number of positive charges, right, which is the number of protons, must equal the number of negative charges. Remember, neutrons don't have a charge, which is my number of electrons. So as long as the atom is neutral, right, as long as that atom is uncharged, then my number of protons will equal my number of electrons. If it's uncharged, charged atoms are called ions, then those two are no longer equal. We can gain or lose electrons. Remember, we can't gain or lose protons because then it's something different, right? It would be charged, but it wouldn't be the same type of atom. It would be something entirely different. So we can change the number of electrons, we just won't do that yet. So we're going to assume right now that they're all neutral. So if you guys are thinking this, I'm super happy with you. What that means then is that this number, this column, and this column are all going to be the same, right? The atomic number is the number of protons, and since they're neutral, it's going to have the same number of electrons. So your numbers that you put into all three of those columns should be exactly the same. So first one, atomic number of 26. So this is where we need our periodic table. So I'm going to grab mine, and I'm just going to find 26. So 26 is right here. 26 is iron. So I'm going to go back, and I'm going to put iron in my table. How many protons does it have? 26. It's uncharged, so how many electrons? 26. And then mass number, remember this was our number of protons plus my number of neutrons. So I'm just going to add 26 to 30, and we get 56. Cool. So I'm gonna let you guys try the rest of the table on your own. So please just pause the video real quick. Go ahead and fill it in. When you're done, hit play again. So hopefully you guys did that. So our second row here, again, these are uncharged. So if they're uncharged and I have 20 electrons, I'm going to also have 20 protons, meaning that my atomic number is 20. If we go out to the periodic table and take a look, the atomic number 20 goes with the atomic symbol, capital C, lowercase a, so calcium. And then this one makes no sense. You guys noticed that when you were doing it, sorry. A mass number of 21, it would have 1 neutron. So I guess if you put 1 here, then great, you did it right. I meant this to be 41, sorry. So I'm going to change it on you, which means this is then 21. Sorry, guys. If you put a 1 there, though, you're absolutely right, giving the information that I gave you. So pretend this was supposed to be 41, not the 21. Sorry. PD is palladium. And if you find that atomic symbol on our periodic table, it has an atomic number of 46, which means it has 46 protons, right? If it didn't, it wouldn't be PD. And since it's uncharged, it's also going to have 46 electrons. And then 107 minus 46 is 61. So it has 61 particles in the nucleus that are uncharged. And I is nickel. So again, looking at your periodic table, the atomic number for nickel is a 28, which means it has 28 positive charges in its nucleus. And then since it's uncharged, outside the nucleus, there's 28 negative charges. And then 28 plus 32 is 60. So it has a mass number of 60. Again, remember, mass numbers are not on the periodic table. So if you went out to the periodic table and you wrote down for your mass number, I'm just looking at my periodic table right now, 58.693, you would be wrong, right? Remember, mass numbers are not on the periodic table. I can't have fractions of subatomic particles. So all of these are always going to be whole numbers.